if you want to get performance. And the reason why you want to use GPUs is performance. So, yeah, you have to know a lot more about your system than on CPU. Alrighty, next part is Ben.
Yep. Thanks. So now we're going to talk about how to program these GPUs. But before we start, I would like to straighten out a few things. It is that I'm going to talk about the programming model. So mostly I'll be talking about how to program these things, and I'll avoid talking about the hardware for now. Another thing is that I would like to make you to make no assumptions about the what is going to happen with the application. So we're going to see how we are going to program against this, basically against a compiler. We are going to program in a particular programming model, but don't think too much yet about how this will be executed by the GPU. We'll come to that later in the afternoon. And also, I will be talking about threads quite a lot. And if you have programmed CPU threads before, don't think that they are in any way similar. You should think of a thread as a parallel programming concept, so a particular abstraction. A thread, in a sense, is the smallest entity that has an instruction tree, you could say. Right? So you can write a program to specify what a particular thread should do, which operations it should perform, and in what order. And that's the concept of a thread in this case. Don't make any assumptions about the weight of a thread or the computational cost of having a thread or context switches or something. But don't consider that for the moment.
Sorry, who has used threads here before on CPU? So not everybody. And parallel programming in general? Yeah, okay, so maybe you have to explain a little bit what a thread is and the difference between a thread and a process, or something.
No, I think that's clear for most people.
Can you consider more like a processes in CPU?
No. That would even be worse. No. Yeah. Yeah. No. We have a single program, and at some point in that program, we will create many threads that will execute a particular function on the GPU. And but yeah, don't make any assumptions about how much it would cost in terms of performance to have a particular number of threads, because the number of threads is going to be overwhelming. That's basically the.
And they do have shared memory, yeah. So
yeah.
So if you look at the difference between a process and a thread, so if you have a number of threads inside a process, and different processes don't share any memory. So if they want to communicate, they have to open a socket or some communication channel, but they cannot read each other's memory. Threads, multiple threads inside a single process, can actually exchange memory values. So you can just read and write each other's data. That's basically the main difference.
This is still called here in the ticket.
Yeah, that's still
to some extent.
to some extent.
Yeah, but I don't know
Yeah.
Yeah.
No, they're not entirely isolated, but they are also not entirely together either.
Very poetic. Yeah, I think that level of detail is you don't have to think about yet.
No, not yet, but we'll get to that.
Yeah,
Definitely. So, okay, so we are going to talk about the CUDA programming model. Like Rob said, CUDA is a very well developed, well documented development environment for creating GPU programs. And also the terminology is a lot more consistent, so I think it's easier to learn in this programming model. So in the CUDA programming model, a program consists of two parts. One is the host part that runs on your CPU, and one is the device part that actually runs on the GPU. Now, the host is mostly responsible for just doing bookkeeping, managing the GPU memory, copying data in and out, allocating, freeing, starting a particular function on the GPU, and then the GPU, the device, is executing those functions that we call kernels. I'm not sure who came up with the name for that. I think it's a bit inconvenient, but let's use it anyway. So these kernels, they are executed on the GPU, by a huge number of threads, thousands, even millions of threads in parallel that will run that particular function. And so you have a particular workload, and usually it's data parallel, so you have lots of data that needs to be processed, and that's what these kernels will work on. And then one of the beautiful things about the CUDA programming model is actually that it allows you to program and to reason on the level of a thread. And that's actually, as you'll see later, quite intuitive. You can write a particular program and you can just say, well, I have this thread and this has a particular ID, and using this ID I know where I need to go in my memory, and I know that these are the values that I need to do my work on as a thread. It's quite convenient to reason about what your program should be doing on the level of a thread. Right, so you're not dealing with very long vector instructions and everything, as you would need to do on a CPU if you want performance. So that's actually something that makes it quite a convenient programming model. So the data management is mostly performed by the CPU, and here again you see this division between your normal machine with host memory and the GPU that is connected to the PCI Express link. And in this entire thing we will call the device. So the GPU is on the device. You can even have multiple GPUs on the device. And there is this device memory. So in the host part of the program is actually managing this device memory, and you can actually write this host part in different programming languages. And for the exercises that we have today, we have created the host part of the program both in C and in Python, so you can choose whichever host language you like. The kernels that will run on the GPU, those are written in CUDA, which is very C-like. It's basically C with a few keywords. So the GPU part is still in C, but yeah, just as a convenience, if you prefer Python, then you can also use Python in the host part. And these are basically what the functions look like, so you can actually allocate memory and free it again in C, and in Python there is this wrapper around CUDA, which is called PyCUDA, and it actually does a little bit of memory management for you, in the sense that it will keep track of your it will do a little bit of garbage collection for you, basically, so you don't need to free explicitly your memory. Now on the host you can also copy the data. So it usually, what it means is that you, let's say, read in some input data from disk, and if you do that, it will end up in your host memory. Then you will allocate some space in GPU memory, and then you will do a memory copy. So you copy the data from the host memory to the device memory. Then you will start the operation on the GPU, and when it's finished, you can basically copy the data back to your host memory and store it to disk again, or show it on the screen or something. That's basically the structure of a simple application. Now, I said that these functions on the GPU, that they would be executed by a huge number of threads, and that's also why we have a hierarchy of threads, and that is basically because we need to organize them in some way. Because we have so many of them, we group them together. At first, going bottom up, basically, we have a couple of threads that are grouped together in what we call a thread block. And these thread blocks can be three-dimensional. And these thread blocks are then again grouped in what we call a grid. So, and grids are typically two-dimensional. I think they can be three-dimensional now these days, but I've never used that actually. Most of the time, having 2D grid is actually enough. But yeah, so you have a hierarchy in which these threads are organized, and that's also where you can see this, these numbers here that basically represent the multi-dimensional ID of a thread. So this would be thread 0 in the X, Y, and Z dimensions within that thread block, and that thread block also has a particular index within the grid. That's actually something that we'll discuss, that we'll need in the first hands-on session actually. So a thread in the CUDA programming model is the most fine-grained entity that performs a particular computation. So in the CUDA programming model, you don't have any vector instructions, at least not for computations. You can declare vector data types, but if you want to multiply to 4-dimensional vectors, for example, then you would need to write out how that multiplication is actually performed. Now, the idea is that you write a program for what a particular thread should do, but all the threads that execute a particular function will have the same program. It is basically through their thread ID that threads know to which part of the data they need to direct themselves, where to gather their input, and where to write their output. That's what we use these thread IDs for. And then, so if you have a very simple example, vector add in this case, we have two arrays, A and B of size n, through which we iterate with this for loop, and we store the result in C, in the array called C. And in this case, we just loop over this from 0 to n-1. So this is basically how you would do it on a CPU in a naive way. And if you were to do this on a GPU now, then you would say, just for the moment, assume that we have a single thread block. Then you would say this would be basically the kernel, the function that will run on the GPU, in which the thread on the GPU tries to locate its ID, which is done through this built-in variable called the thread IDX, stands for thread index, and then the x value of that, so that's the index in the x dimension. At this point, we only have numbers in one dimension, so we have just a one-dimensional thread block, and we only have one thread block in this function. And what we are now doing is that all the threads will then execute one addition, basically, and store that value in C. Now, the idea is that all the threads are executing the same program, but they will see different values for this thread index. And that's why, if we create enough threads, say we have n threads in this thread block, then all the operations that would have been performed by this loop are now also performed by this function on the GPU if we create a sufficient number of threads. Is that clear?
And if the n is bigger than how many threads you can execute in parallel?
Well, the number of threads that you can actually run on a GPU is really, really high. So you'll never run into that. But what we will, it's a good question, because we will run into the fact that a thread block can actually have so many threads. So this is actually still using one thread block, this function. And the idea is that if you want to do more than that, and a thread block at the moment is limited to 1024 threads. So if you want to, if you have an n that is bigger than 1024, you will have to use multiple thread blocks. And that's actually my next slide. So, good question. Threads will be grouped into thread blocks, which will allow you to work on larger problems. And the idea is that these thread blocks are actually also numbered, also with indices again. So this is called a block index. And again, we have these x, y, and vz to have an index into a particular dimension with the thread block. Now that's another nice point. We can only create threads in as a multiple of a particular number of thread blocks. Right? So we define how many threads there are in a thread block, and we define how many thread blocks there will be. So the total number of threads is always a multiple of those. And that may actually be a little bit larger than the problem size that you are working on at that particular moment. So that's something to keep in mind when writing your functions. And there are actually a few more built-in variables. We also have block dimensions in X, Y, and Z. So that's something that you sometimes need. It can be convenient to know as a thread how many threads there will be inside the thread block. And similarly, sometimes it's relevant to know how many thread blocks there are in total. And of course, you can also multiply these numbers to get the total number of threads. And that's sometimes you actually need that. Actually, in the last hands-on session, we will need this. Because there we will have a kernel in which all threads are cooperatively working together to a particular goal. So that's why these values are basically present. And one other thing is that in contrast to these indices, all the threads will see the same values, of course, for these block dimensions. And it's also that you can only have one, you'll define the size of the thread block and how many thread blocks there are. You cannot have different sized thread blocks within a single function. It's just one size. And if you need less for some reason, then you can always have if statements and make sure that only the threads that need to do something actually do something. Because you can, of course, write if statements on these indices. We're actually building up to the first hands-on where we will actually use this. So this is a bit of C code to show you what is actually needed to start a particular function. So in the host program, so this runs on the CPU, you actually define the number of threads within the block. In this case, we're using this built-in struct that the CUDA programming model offers us. It's a dim3, it's called, but it's just a single struct of 3 integers called x, y, and z. And basically, with this, you define the size of the thread block in these dimensions. And then also we have the size of the grid, which is basically the number of thread blocks into a particular dimension. And with this very peculiar 3, what you call them, parentheses, syntax, you actually start a function. So this is assuming that we have a function called vector add, which is actually a kernel that we can run on the GPU. And this is to tell the CUDA runtime how many thread blocks we have and what the size of these thread blocks is. And this will just be the arguments to the GPU function. So most likely these are actually pointers into GPU memory, so the device memory, so that then the GPU function knows where these input and output arrays are actually stored. And what we can do after we have called this kernel, after we've launched this kernel, we can wait again on the CPU for this kernel to complete, because that's another important thing. Launching a kernel like this is always asynchronous. So the host program will not wait for the GPU to do its processing. It will just continue. So you can also have you can also start multiple kernels after each other. And then only when you do something like device synchronize, then you will actually synchronize the host thread with the device part of the program again. So you have of course, the program is divided into a host and a device part. And only when you call something like this, you block the host until all the pending operations on the device have completed.
Question?
Yeah.
So if I launch multiple things on the GPU that depend, so the first one includes C, and then the next one uses C to do something else, then it will wait on the GPU for the result to be there? Or?
Yes. So what's actually nice in the CUDA programming model is that there is basically a hidden stream, which is called the default stream. And in this, if you launch a kernel like this, it will be executed on the default stream, and within a stream, all the operations that you schedule to the GPU are actually in order, right? So they are in program order. So yeah, if you do a vector add and then another vector add that also uses C again, then that will definitely be one after the other. If you want to actually specify that 2 kernels can happen independently, can be executed independently, then there is there is a bit of API that you can use to create these streams explicitly, and then also when you launch a kernel, you can have a bit more parameters here within these brackets, and then you can specify which stream this kernel is to be executed, and you can also wait on a particular stream. So that's all API for that. Yeah. Okay, so we're now moving towards the first hands-on session. This slide is a bit about the setup that you will need to do to be able to run the exercises on the DOS5. So we're now going to use the DOS5. Everyone has an account, I believe. And these are a couple of things that you will need to set up. If you would like to use the Python host code, then it's, I would recommend that you follow these instructions. This is actually installing a Python environment in your home directory. So if you already have something like that set up, then you can also use the Python environment that you are already using, of course. Don't forget that you will need to do that first part anyway. So always do the top part, and if you would like to use Python as a host part, then you can do the bottom part.
Question.
Yes.
I'm not using Miniconda, but are you using Python 2 or 3?
I would recommend Python 3, but it doesn't really matter. Yeah, my host code is Python 3 program. Yeah. Yeah. Yeah, but with if you add from future import print function, then that will work. Then I think most of them will be compatible with Python 3. Yeah. Okay. Yeah, so if you already have a Python environment, then just make sure that you probably have NumPy then, but you can do pip install by CUDA. Before you do that, make sure that you have module load CUDA 80, and that you have loaded that module, because only then by CUDA will actually look for your CUDA installation. So. If you have this setup completed, feel free to move to the next slide, because that's where the hands-on session is explained as well. I will leave this up for people to type over for now. So the idea is that you can go to the Git repository, the same one as where you got the slides. Clone that repository from your DOS account is the most convenient. If you just type git clone on the DOS. And then you go into the directory called vector add and just look at the code, make sure you understand everything in the code, and the exercise that you will need to do is also in the code, so you can just look at the.
Actually, if you want to save your work, it's better to fork the repository first and then clone it, because then you can push to your own repository.
Well, you can also do that later, I guess.
You could do it later, but yeah.
It's
easier if you do it directly.
yeah, well, if you rename the origin.
Plus you get no forks, which is
Sure, fork it. Don't forget to star and watch it.
So who's going for Python and who's going for CUDA C? Python? C?
If you need someone in mind, you need that.
No. So it was actually funny when we gave this course in December for a couple of PhD students in computer science. I actually expected most of them to go for the C host code, but it appeared that, well, I guess that we have the same division.
Yeah,
So,
sure.
about
Python,
80% was interested in using the Python host code. So.
So much for computer science.
Yes. Very good, you could do that. Number 3.
Maarten, you have a question?
I made a Slack channel actually
Yeah.
for the course.
We don't have a hashtag yet.
You don't want to talk out loud?
Oh, which is really handy, but not everyone here is on Slack yet, so make a Slack account, because we share things on Slack all the time in the eScience Center, so
Yes,
making a Slack account is actually a good idea. I hope you too.
I have one. I have 3.
Well, I used to be on Slack as well, but I found it
So
very
which-
inactive, so I
Which
stopped
Slack do
moving
you
it.
mean?
The Netherlands eScience Center Slack.
Okay. What is the exact name of this? NLESec?
Yes.
NLS.slack.com.
Yeah, that's where you need to SSH. You have received this email from Kees? So you can open the terminal.
Yes?
Yeah, in your virtual box. Just open the terminal. And you can do SSH. And then the FS
Dat is het.
then you will be prompted for your login and password. Yeah, so guys, during this hands-on session, feel free to grab coffee. Coffee!
Ja, dat is het additionele manier, maar niet de
Echt hoor?